Alright guys, welcome back. In today's question we have this sailor that is being rescued using a boatswain chair that is suspended from a pulley that can roll freely on the support. So from here, rolling freely means there is no friction, so we don't consider any friction. And it's supported by cable ACB and is pulled at a constant speed. Another important part of this question, meaning that we are in a constant speed, which means the sum of all forces, which is equal to mass time acceleration, constant speed. There is no acceleration, therefore the sum of all forces equals zero, and we will be in equilibrium condition. We know that the two angles alpha and beta are 30 degrees and 10 degrees respectively, and the combined weight of the chair and the sailor is 900 Newton. So in the A part of the question, we need to find the tension in the support cable ACB, and in the B part of the question, we need to find the tension in the traction cable CD. So basically, we need to find two tensions at the end of this question. I'm going to start with the free body diagram as always to see what we have. So let's set our x and y exactly in the center of the pulley or point C. So this will be our x and y. We have one single cable ACD, meaning that the tension in that cable will be the same. So in this side we have, let's call it TACB. We know this angle beta is 10 degrees, and we will have the same tension here. Again, TACB. This time the angle is alpha, which was 30 degrees. And we have another tension, which is the tension in cable CD. Let's call it TCD. And the last force that we have is the weight of the sailor and chair, which is 900 Newton. So that would be pretty much everything for our free body diagram. As I mentioned earlier, we are in the equilibrium condition. We are moving with a constant speed. There is no acceleration, so the sum of all forces will be zero. So let's start with sum of all forces in x direction. So we have the cable TACB times cosine of 10 degrees. We have again TACB, this time in a negative direction since we are in the opposite direction of x. So this time we'll have cosine of 30 degrees, and for TCD, we have the same thing since these two tensions are parallel to each other. So TCD also makes 30 degrees angle with the horizontal. So we have TCD this time cosine of 30 degrees. That's pretty much what we have for our x equation. And from here we can find TCD based on TACB. And if we do that, we'll get 0.1372 TACB. So let's move on to the sum of all forces in y direction. So in here we have again the y component of TACB will be positive. This time we'll have sine of 10 degrees. Same thing, we have TACB on the left side, which will be the sine of 30 degrees. And we also have TCD sine of 30 degrees. And the last one would be the weight of the sailor, which was 900 Newton. So if we substitute the first equation in the second one, what we will get is, so we'll have TACB sine of 10. So if we factor TACB, we'll have sine of 10 plus sine of 30. And for TCD sine of 30, we know it's 0.5 TCD. This will be equal to 900, and sine of 50 plus sine of 10 would give us 0.6765. So now we have TCD based on TACB. So we're just gonna substitute what we found in the first equation, which was 0.1372 TACB equals 900. And from here we can find TACB, and that would give us 1,1212.56 Newton. We found the first one, and now that we have TACB, we know TCD will be from the first equation again, 0.1372 times 1256, and this would give us 166.3 Newton. And that would be the final answer for this question. So a couple of main messages in this question. First thing, since the pulleys can roll freely, there is no friction in our free-body diagram and equations. We are in the equilibrium condition since we are going at the constant speed, and in the cable TACB will have the same tension, and we need to consider the tension in both sides, which we called it a TACB. And at the end we'll end up having two unknowns, and we'll have two equations which we can find.